Have you ever stopped to think about how fast chemistry actually happens? I mean, think about it. An explosion is over in a blink, but a piece of iron can take decades to rust away. This is the amazing world of reaction kinetics, and it's all about the secret speed of chemistry. So let's dive right in.
And you know what? We're going to crack this whole thing open by looking at a tiny, beautiful mystery. The flash of a firefly. It's not magic, it's pure chemistry, a perfectly controlled reaction. But how in the world does it work? And maybe more importantly, how do they turn it on and off, just like a light switch?
To get to the bottom of that little flash of light, we first have to understand the basic rules that run all chemical reactions. It turns out, the firefly's biggest secret is hidden in the fundamentals of chemistry itself. And the range of these speeds is just staggering, right? You've got iron that can take years and years to rust, while the methane in a gas stove burns almost instantly. That huge difference is exactly what reaction kinetics is all about. Okay, so let's start with clue number 1. Before anything can happen, before any new cool substance can be formed, the basic ingredients, the molecules, they have to actually meet each other first. This whole idea is the absolute foundation. It's called collision theory. And honestly, it's about as straightforward as it gets. No collision, no reaction. The particles literally have to bump into each other for anything to happen at all.
You can just picture it, right? You've got these separate molecules just zipping around, doing their own thing. They get closer and closer, and then wham, they collide. That's the first, absolutely essential step on the road to a chemical change. Okay, but that brings up a really good question, doesn't it? In any glass of water, in the air you're breathing, there are billions upon billions of collisions happening every single second. So why isn't everything just reacting all the time? Why doesn't a log just instantly burst into flames? Clearly, just bumping into each other isn't the whole story. And that brings us to the next, and honestly, the most crucial piece of the puzzle. It turns out not all collisions are created equal. To get a reaction to actually go, you need the right kind of collision. And it's a pretty stark difference. Most of the time, the molecules just kind of bounce off each other. No harm, no foul. Unchanged. But for an effective collision, the one that actually makes something new, two things have to be absolutely perfect: the angle and the energy. The molecules have to hit each other in just the right orientation, kind of like a key fitting perfectly into a lock. And they've got to collide with enough oomph. This minimum amount of energy is called activation energy. Think about it like this. You're trying to push a giant boulder over a hill. That initial push you need just to get it to the top, that's the activation energy. Without enough of it, the boulder just rolls back down and the molecules just bounce off each other. All right, so we've got collisions, we've got the right angle, and we've got enough energy. We're getting close. But there's one more little secret we need to uncover before we can solve our firefly mystery. Even the simplest looking reactions are usually hiding something. So you look at a reaction like this one. One molecule of hydrogen gas plus one molecule of iodine vapor makes 2 molecules of hydrogen iodide. Seems pretty simple, yeah? One thing meets another thing, and you get a new thing. Yeah, or so it seems. That simple equation, it's definitely not telling the whole story. So here's the big reveal. Most chemical reactions, they don't just happen in one big dramatic moment. They happen through what's called a reaction mechanism, basically a whole series of smaller, simpler steps. That final equation we write down is just a summary of the beginning and the end, not the actual journey. And understanding that journey is the key to controlling the whole thing. And now we have all the pieces. Collision, energy, those hidden steps. We've got everything we need to finally solve the mystery of our firefly. Let's head back to where we started. That incredible glow is a process called bioluminescence. It is nature's perfect example of everything we've just talked about. A chemical reaction that's been fine-tuned to produce light with almost perfect efficiency. So here's how the firefly pulls it off. First, the reaction needs oxygen to even get started. But it also has a secret weapon, an enzyme called luciferase. This enzyme is a catalyst. Remember that big hill we had to push the boulder over? Well, this enzyme comes along and basically bulldozes that hill down to a little speed bump. It also lines the molecules up perfectly for collision, making the reaction incredibly fast and efficient. And the flash? The firefly controls the reaction by controlling the oxygen. It lets a little oxygen in to turn the light on and cuts it off to turn it off. Blink, blink, blink. So you see, The firefly is so much more than just a bug with a light. It's this tiny, flying chemical engineer, a true master of reaction kinetics. It has complete and total control over the speed of its own chemistry, starting and stopping a reaction whenever it wants.
By understanding these rules, we cracked the firefly's code. And it just makes you wonder, right? The question isn't just how a firefly glows. It's what other secrets of nature are just waiting for us to figure out. What reaction will we learn to control next?